Welcome back. Today I want to talk to you about Riemann sums and the fundamental theorem of calculus, okay? And I want to start where we left off and recall the way that I find the area under a curve between A and B, okay? So let's just remind ourselves we have a function, okay? And we have a point A and we have a point B. And what we said is we want to find the area between the two, so let's chop this up into some pieces and then make rectangles we were using the right hand side to find our functional value or our heights of our rectangles. We use the right hand side to do that, and we get an approximate area. And as n goes to infinity, we get the actual area. And we always used the right side of the rectangle to calculate the height. Just by the way that I set this up, this is the right-hand endpoint that I'm using. It doesn't have to be the right-hand endpoint. It could be the left-hand endpoint. It could be the midpoint. There are lots of ways you could go here, but it has to be something. Okay, and so we could generalize what's going on here and make it a little more clean. So the first thing that I want to do is say that we could make this more clean, and the general way of looking at this is what we call a Riemann sum. So let me talk a little bit about Riemann sums real quick. So Riemann sums. And this is how it's going to kind of go. We've got a curve over here. And we've got a point A, we've got a point B. The first thing we're going to do is we're going to break up the interval from A to B into some pieces. Now, they don't have to be equal pieces. The way that we looked at it in our last lecture, they were always equal pieces, and I called those pieces delta x. The width of each piece was delta x. It could be any width. So the first thing we're going to do is we're going to partition this into some pieces, and then I'm going to define something that I'm going to call the norm of P, or the norm of this partition. Okay, and the way that I'm going to find this special number, let's just call it, which I'm calling the norm of this partition, is I'm just going to take the maximum value of all of the delta x sub k's. So remember the widths here, this width and this width and this width, all of these widths, they could be different. I didn't say they had to be the same. But what I'm going to call norm of P is the big one, whichever one's the biggest of those widths. I'm going to call that the norm of the partition. Okay, so once I've defined this thing called the norm of the partition, then I'm going to choose an arbitrary number from each subinterval called x sub k, and I'm going to call it x sub k star. And sometimes it gets kind of like, man, that is a lot of stuff to attach to the x. There's a k, there's a star, and why do we put the little star up there? The little star is just saying he's a special point. He's the special chosen point in that interval. So in this first interval between, let me maybe draw it a little bigger. So here's A. A is also known as x sub 0. Here's x1. Between x0 and x1, I choose a point. And that point, I'm going to call him x sub 1 star. Okay? and he's going to be the guy that gets to represent everybody as the height of the rectangle. So this will be my first rectangle that I'll add. Then, maybe up here is x2. So somewhere in between these two, maybe right here, I call this guy x sub 2 star. And he gets to represent that whole interval in terms of the height of the rectangle. Now, notice I didn't choose the right endpoint. I didn't choose the left endpoint. I'm not necessarily choosing the midpoint. Just choose somebody. Okay? So we're making this very general. So then, once I've chosen these special star points, let's add up all the rectangles. All right? So I'm going to add up all these rectangles, and I form this sum. I'll call it R sub n, which is going to be the height of the first rectangle, which would be f of x sub 1 star, times the width of the first rectangle, which I call delta x sub 1, the width of the first rectangle, plus the height of the second rectangle, so the functional value at the second special point, times the width of the second rectangle, which is delta x sub 2, plus, and so on, plus the very last rectangle, the nth rectangle, would be f of x sub n star times delta x sub n. If I wanted to write this as a sum, then I'd say that this nth Riemann sum within in rectangles would be the sum, k going from 1 to n, of f of x sub k star times delta x sub k. Now, if this is an estimate, because right here I've just added up in rectangles. If I wanted to add up infinitely many rectangles, then what do I need to do? Well, it's not just so easy to say, well, now let the number of rectangles go to infinity, because I don't know that they're necessarily getting small. Because you could have a lot of rectangles and still have one really big rectangle. So what we want to say is, I want the biggest rectangle to get small. And so what we're going to do is we're going to say, if we want the actual area here, then I want to take the limit as this thing that I called the norm of the partition goes to 0 of sum k going from 1 to n of f of x sub k star times delta x sub k. Now, in the limit of the sum that I started with, the definition that we used in our last section, that is a Riemann sum. So this is just the general form of the Riemann sum. The one that we used last time is a specific form of a Riemann sum. They're all Riemann sums. But this is just showing us I could take the right-hand endpoint, I could take the left-hand endpoint, I could take a midpoint. It just doesn't matter. It all works. Okay? So now let's define something. I'm going to actually write down a definition for what we call the definite integral. Okay, and the definite integral is the following. If f is defined on the closed interval AB, we say f is integrable on the closed interval AB if I is equal to the limit as the norm of the partition goes to 0 of the sum k going from 1 to n of f of x sub k star times delta x sub k exists. This limit is called the definite integral of f from a to b. Okay? And this is the way we write a definite integral. Instead of writing this big mess every single time that we write a definite integral, we kind of have a shorthand for our definite integral. So I is also equal to, we write it this way, the integral from a to b, a being where you start, b being where you end. So these are called my limits of integration. Where do I start? That's the bottom number. Where do I end? That's the top number of the function that I am trying to find the area under, dx. So this guy up here and this guy down here, that's the exact same thing. Whenever I write a definite integral, I really mean this limit up here. Okay, but this is very, very complicated, and as you've seen in the last section, pretty hard to compute in general. And that brings us right into our next subject, and that is what we call the fundamental theorem of calculus. Let's look at the first part of the fundamental theorem of calculus. All right, so let's read through it really quickly. It says if f is continuous on the interval a to b, and capital F is any function that satisfies that the derivative of capital F is little f of x. In other words, capital F is an antiderivative of little f of x. Then the integral, the definite integral from a to b of f of x dx is capital F of b minus capital F of a. Now remember, we've done these problems and they're hard to find like the limit of a sum. So finding the limit of a Riemann sum, that's hard work. This is saying if you know the function's antiderivative, plug in 2 points, those 2 points just happen to be the endpoints, and you're done. So all you really need to know in order to compute a definite integral is an antiderivative for the function. And if you do, life's wonderful. And so the fundamental theorem of calculus is a big deal because it says that this problem of finding area under a curve is really boiling down to, can I find an antiderivative for the function? Okay, but this is such a big deal, this fundamental theorem of calculus, that I really feel like we need to prove it. So I want to prove the fundamental theorem of calculus for you really quick. Okay, so take a look, read it over one more time, and let's get into the proof. All right, so proof of the fundamental theorem. First of all, what we do, and we know we do this, we've done it already, is we define a partition of the interval. So I'm going to let capital P be our partition, and I'm going to break this up into x1, x2, x3, and so on. We have all the way up to x sub n. And this is going to be a regular partition with subinterval lengths delta x is equal to b minus a over n. So what I'm going to do is, what I mean by a regular partition is I mean all of the lengths of the intervals are the same. Any Riemann sum will do. I might as well take one that is nice. So I'm going to make sure that all of the partition lengths are the same. Okay? So all the lengths are b minus a over n, and we're just going to call that delta x. So note that this function capital F, if it exists and we can find this special antiderivative, it satisfies the conditions of the mean value theorem, okay, on each interval from x sub k minus 1 up to x sub k. Okay, so what we're saying is that the mean value theorem works all over the place on this function, and specifically it works where the endpoints are the edges of our partition. So by the mean value theorem, we have that there exists, we'll call it x sub k star in x sub k minus 1 to x sub k, for which capital F of x sub k minus capital F of x sub k minus 1 over x sub k minus x sub k minus 1 is equal to f prime, that's a prime, of x sub k star for some value c by the mean value theorem. So we've got this. This is true for every single interval. But another way that I could write this, notice what this guy is. X sub k minus x sub k minus 1, it's the length of one of the little partition intervals. In other words, this guy is really what we're calling delta x. Okay, so this thing on the bottom, that's delta x. So we could multiply both sides by delta x, and if I did, I'd get the following. So let's multiply both sides of the equation by delta x, and I get that f of x sub k minus f of x sub k minus 1 is equal to f prime of x sub k star times delta x. And that's true for every value of k. If that's true for every value of k, let's write it out for a few values of k. So let's say that k is 1. So I get that capital F of x sub 1 minus capital F of x sub 0 is equal to capital F prime of x sub 1 star times delta x. I also get that f of x sub 2 minus f of x sub 1 is equal to f prime of x sub 2 star times delta x, and so on. And I get that f of x sub n minus f of x sub n minus 1 is equal to f prime of x sub n star times delta x. And now what I would love to do is add all of these guys together. If I do, something kind of special happens. Notice that if I'm adding all of these, right here I have an f of x sub 1, and here I have a negative f of x sub 1. Then I have an f of x sub 2, and a negative f of x sub 2 would be the next guy. And finally I'd get an f of x sub n minus 1 and a negative f of x sub n minus 1 if I added all n of these equations together. And what am I left with? I'm left with f of x sub n minus f of x sub 0. And on the other side, I get the sum k going from 1 to n of f, capital F prime of x sub k star times delta x. Now, what is the derivative of big F? It's little f. So these are just little f's. So let's write this again, but let's simplify it even a little more. X sub n, that's just another way of saying b. So this is just capital F of b. Minus x sub 0, that's just another way of saying a. So this is f of b minus f of a is equal to the sum, k going from 1 to n, of little f of x sub k star times delta x. Now what I want to do is, these are the same thing. Both sides are the same, so I could take the limit as n goes to infinity of both sides of the equation. Let's do it. So I get the limit as n goes to infinity of f of b minus f of a, and that's equal to the limit as n goes to infinity of the sum, k going from 1 to n, of f of x sub k star times delta x. All right, this side, that's just a constant. The limit of a constant is a constant, so I get f of b minus f of a. And on the other side, that's a Riemann sum. Well, a Riemann sum, that's a definite integral. So this is the integral from a to b of f of x dx. All right? So this is what we call the fundamental theorem of calculus. And that is what I have boxed in right here. And that is that if you want to find the definite integral of a function little f of x, you just need to take the antiderivative, find the antiderivative and plug in b, then subtract that same antiderivative plugging in a, and it gives you the definite integral. That's amazing. So somehow in the endpoints of an interval, the information is contained about how much area there is under the curve. That's very odd, but it seems to be true in some sense. So that's what we call the fundamental theorem, and that's the first part of the fundamental theorem. Now let's talk about the second part. Now for the second part of the fundamental theorem of calculus, and this one I'm not going to prove, I'm just going to present it to you, and then we're going to talk about what it means. The fundamental theorem's second part says, let f of t be a continuous function on a closed interval ab, and then define the function capital G by this integral. So capital G is the integral from a to x of f of t dt. Then we can say that capital G is an antiderivative of f on the interval, and that if I took the derivative of g, now remember g itself is an integral, so if I'm taking the derivative of g, then I'm taking the derivative of an integral. And if I take the derivative of an integral, what pops out the other side? Well, you would expect the original, because you're taking the derivative of an antiderivative. And in fact, you do get f. But it's not f of t, it's f of x. Okay? And this is where you have to be just a little bit careful. So what I'm doing actually here, and this is what's so simple about the fundamental theorem, is that I'm taking this x value, plugging it in wherever I see a t, and that's what comes out on the other side. And we'll see some specific examples of this. Now, what I could also do is I could take this integral, compute the definite integral, then take the derivative of that function with respect to x, and what would come out is f of x, little f of x. And so either way works. This is just kind of a shortcut in order to quickly take the derivative of a definite integral. Okay, and we'll see some homework problems that do this sort of thing.